Hey guys, today we are going to solve the fourth problem in the ongoing Leetcode contest. There's still 14 minutes left, so I decided to start recording the cast. So solve the fourth problem. Um, so let's understand the problem first. It says, so we are basically given a graph, a weighted graph, and we are given a set of edges in the graph. So now every edge will represent a non-negative weight. Um, sorry, it can be a non-negative weight up till 10 raised to 5, and then you are given some queries. Basically, in this query vector, you will be given two vertices between which you have to find the distance, and the queries can go up till 10 raised to 5, and your graph can have edges up till 10 raised to 5 as well. So number of edges can be 10 raised to 5 as well, and the number of vertices is also can be up to 10 raised to 5. The only twist over here is that when you let's say want to find a distance between a node u and a node v, then instead of doing a normal addition between their weights, let's say uh, there are two vertices 1 and 3, and there's a graph from 1 to 2, there's an edge from 1 to 2, and there's an edge from 2 to 3, and the weight of the edge from 1 to 2 is, let's say, 2, and the weight of the edge from 2 to 3 is, let's say, 3. Let me draw that. Let's say there's a graph like this, right? And the weight is this. Then in a normal world, the distance between 1 and 3 would be 5, right? But here, as per the problem, it's given that whatever walk you do from u to v, you just have to do an bitwise AND of the weights involved in that walk. So basically here the distance between 1 and 3 as per our new problem would be 2 and 3, which is nothing but you have to do an AND between these two. So basically this is a 2, this is a 3, let's do an AND, this will be 1 0, and this will become 2. So distance between 1 and 3 is 2. And now you have to find the minimum distance between, so you will be in the query vector, you will be given source and target, and you have to find what's the minimum distance between S and T, as per our new definition of distance, which is the bitwise AND of the edges that you traverse between S and T. So how to solve this problem? So the first thing to notice over here is that and bitwise AND is a decreasing operator. It's a decreasing function. So let's say you are given you're doing the bitwise AND between these numbers, and then you do a bitwise AND between these two numbers only, and all of these numbers are greater than or equal to 0 and can go up till infinity, let's say. So then the more numbers you do a bitwise AND of, the less the answer will become. So basically a1 and a2 will always be greater than a1 and a2 and a3 and a4. And a simple proof for this is that once you set a bit to 0 because of an AND operation, it can never go back to 1. So that so basically what we are saying is, the more numbers we have, let me write that down. We are saying that the more numbers we have, the lesser the answer will become in a bitwise AND operation. Okay, so basically what that means is that when you are traveling from source to target, and let's say you have all these nodes in between like this, you can have some nodes like this, you can also have multiple edges in the graph, and let's say you're traveling like this. Let's say this is the connected component of S and T. That means that S and T belong to the same connected component, and these are basically the vertices or the edges between them. So as per our definition, as per our definition over here, it says the more numbers we have, the lesser the answer will become in bitwise AND operation. That means that our goal should be to do bitwise AND of all these edges. So these are the edges W1, W2, these are these weights, W4, W5, W6, blah blah blah, so up till Wn. So our answer for D and S and T would be bitwise AND of all these edges, of this edge, of this edge, this edge, this edge, this edge, this edge, all of them, just do it bitwise AND, and that would be your minimum distance. Because the more numbers you join to the AND operation, the lesser the answer will become. It's just optimal to do a bitwise AND of all these edges in the connected component. So algorithm will look something like this. Check if S and T lie in the same connected component, right? So this is step 1. Oh, wait. Right? Okay. Step 2 would be to if they do, check if S is equal to T, that means that you don't have to travel at all and the answer is 0, right? And if they are the same connected component, return bitwise AND of all edges in the component, right? So how do you calculate the bitwise AND of all the edges? So basically, if you notice, we will just do a BFS, that is a breadth first search. So inside a breadth first search, when let's say you start from a particular node, then when you are trying to do a breadth first search, it will always discover the nodes that are connected to that node that we are starting from, and then it will go to each of these nodes, right? And then it will do a separate breadth first search from all of them. It will traverse to the breadth of these nodes, right? So all of these nodes will be again in the queue. So basically, we are discovering the whole component via doing one breadth first search starting from this particular node. And how to distinguish between when we're to push in the queue of the breadth first search or not, what we can do is we can take the node and its weight as an identifier. So if your this combination of node and weight has not been seen before, not been seen or whatever was visited before, we just visit it. Just visit it and update the answer by doing this for that component. Okay. So basically the idea here is that, let's say your query contains this node and this node, then because they lie in the same connected component, their answer will always be the bitwise AND of all these edges. So basically, if two vertices lie in the same connected component, their answer will always remain the same. The minimum answer will always remain the same. That's the idea. And we are doing this as an identifier here because what we want to do is that let's say your graph has multiple edges like this, right? And if I only use the normal identifier, like I maintained a visited array of nodes, on only nodes, and not this where it says visited array of pair of nodes and their weights. Let's say we maintain this, let's say we didn't maintain this. Then what it will do is, let's say the weights are 1 and 2, this is node number 1 and 2. Okay, so when you start a BFS from here, it will discover this node and that's it. Because this is visited, this edge will get disregarded. but we also want to account for this edge as well, because let's say let's say your node was weight was 3 over here. If you only store nodes in your visited array, then the answer would be just 3, right? Because this edge was never traversed, because we already traversed 2, and when you pop this 2 from the queue, it will say that 1 was already visited. I don't need to visit this one at all. But if you have a visited array which stores both a pair of node and its weight, that will say that okay, let's visit 2 and 3 first, and then it will say from 2 we can visit 1 and 2. This guy was not visited before, right? Because it has a unique weight combination. So that's why it will also visit this particular edge, and it will do a 3 and 2. Basically, the idea is to just visit the maximum number of edges we can, not the maximum, basically all the edges in the connected component. That's the idea. So let's jump to the code. So here's what I'm doing with the code. First, I want to construct a graph out of these edges. So I construct a graph like this as a normal adjacency list, and then I initialize some variables over here. Comp is basically to do this stage where we want to check if S and T lie in the same connected component. So comp of I would be the ID of the connected component in it. I is the node. Then I store an answers array, a visited array. So this visited array will allow me to check if I can do a BFS from that node or not. So it's that visited array. And inside the queue, I will use a different BFS array. I'll just come to that. Now we have a queue and the ID. So if let's say we traverse over all the nodes. If you're not visited one particular node, we want to do a BFS from that node, and we want to discover all the connected nodes from that particular node. So I just push that in the queue. I mark that node as that we visited that node, and now this is the pair of visited node comma weight edge array that I was talking about. So it's just a modified version of the BFS. So over here, I just pop the node, and then I set the connected component ID of that node to this ID. So because when you're traversing in a BFS fashion, the ID of the connected component will remain the same as the ID of this component. So basically we have to just set the ID, and we'll say that they lie in the same connected component if the IDs match. That's all that we are doing over here. So initially ID was 0, and you start from the 0th node. Then if all the nodes that are reachable from 0, they'll have the same ID set to 0 like this. Okay, just do a queue.pop, a normal BFS, and we visit all the nodes that are starting from this node that has been popped. And now we check if inside our set of pairs, if that particular node, that particular combination of node and weight has not been visited. So if its count is 0, then we do want to visit it, and visit as in we'll push that node inside this set of pairs, just insert it, and we'll do our answer thing over here. If let's say the answer was initialized to 1, so it's -1. If it's -1, just take the weight of that edge, or else if it's already in the process, if it's already not initialized to -1, we just do a shorthand AND operation over here with the weight that we are looking at currently. So that's all we have to do here. And after you are done doing this BFS, we just store the answers. So basically for that component, we have to store the answer also, right? So the ID of the component was ID. So inside the answers array, it's a very initialized to a size of 2, and I just do an answers of ID equals to answer, whatever the answer it is. And I just increment the ID by 1 to go to the next component in the graph. So overall time complexity would be O of n log n. And over here to just return the answers, I initialize this return vector. And if the nodes in the query are the same, just it's a 0 distance. Else, if their connected components are the same, that is their IDs match, right? Then just push back the answers of ID inside this return vector. Else the components are not reachable, and just push back -1. So that's it. Hope you guys like the explanation and do share your thoughts in the comments. Thank you for watching. Bye.